Yeah. Okay. Slideshow. Okay. So, any question from this side? So, as we said, we finished our chapter 5, which is about orthogonality and where we define inner product, so we can define geometry on the vector space. We define angle, perpendicular, and also null basis, etc. on vector space through this inner product structure, always also defined by null. Okay, but today, as we say, we are going into a different topic. So this might heard from other places already. It's about eigenvalues, and hopefully the start of today will be a review of your high school things, high school, high school math. But anyway, so what are eigenvalue and eigenvector? So we just start from a definition. So eigenvalue and eigenvector are spatial vector that happen when you multiply a matrix. Okay, so this whole chapter we are back to n by n matrix. So basically, this is what we call linear operators in chapter 4. Okay. Anyway, so we're back to n by n matrix. So we are transforming from Rn to Rn. So we are transforming inside the same space. Okay. And if you are in R, if you are in this same, if your starting space and end space is the same Rn. Okay, this one is starting n. But anyway, so if n by n matrix, then Ax can have special properties such that Ax equals lambda x. Okay, so this only happens when n equals to m because you need the dimension of this equal to dimension of this. But anyway, if Ax equals to lambda x, so x getting multiplied by a is still x, but just with another constant vector lambda here. Then x is called the eigenvector or characteristic vector of this matrix A. And this lambda value here is the eigenvalue or characteristic value. Okay? And so this is a way to analyze the square matrix A. So later on we're going to try to find the eigenvalue and the eigenvector of the matrix A. Okay? And finding this is very useful because it tells you how to do multiplication on something. Okay? So just from here you see that the multiplication of matrix on eigenvalue is very easy. You just get a constant vector. But first you need to know the vector is eigenvector. But anyway, let's go into an example to see how this happens. So here we're given a matrix A and we are already given eigenvector here that we know is an eigenvector. Okay, so A is 4 minus 2 1 1 matrix and A is 2 1. And then we just do matrix multiplication to check that Ax is actually some constant multiple of x, okay? Or a scalar multiple of x. So Ax equal to 4 minus 2 1 1 2 1, and the first register become is A minus 2 equal to 6, and second register is 2 plus 1 equal to 3. So the 6 3 is 3 times 2 1, so it's 3 times x. Okay, and so in this example, the eigenvalue is 3 times here. So this 3 is the eigenvalue of A against x. So this x21 is an eigenvector of A, okay, and with eigenvalue 3. So eigenvalue and eigenvectors are paired together. So yeah. And each eigenvector has one eigenvalue, but one eigenvalue might have different eigenvectors. Okay, and Also, from just finding one eigenvector, you can find many eigenvectors. So because everything is linear. So say, excuse me, yeah. So say if you have instead of 2, 1 here, you have 4, 2, then you multiply x by 2, then everything will get multiplied by 2. Okay, and here is more algebraic to say this. So if you instead of multiplying a with eigenvector x, you multiply with alpha x, and because everything is linear, then you can just take the alpha outside. Okay, and then it's alpha times ax, and ax is lambda x, and so it's lambda times alpha x. Okay, so if x is eigenvector, then the whole linear space spanned by x is the eigenvector. Okay, with the same eigenvalue lambda. Okay, and yeah. Here is the example. So if we change x to 4, 2, and then you see all the calculation here just get multiplied by 2. So instead of 6, 3 here, we have 12, 6 here, and yeah, 12, 6 is 3 times 4, 2. And so you got the same eigenvalue 3 here. Okay. And so that's about example 2. Then we kind of derive the next thing under here. Okay, and so here we are just given the eigenvector here, and so given eigenvector, so if someone already told you is eigenvector, you can check it is eigenvector by doing this multiplication, and see whether it's actually proportional to your eigenvector, and you get eigenvalue here. But if you are just given an A and you want to find the eigenvalues and the eigenvectors, then what you can do is you start from this equation. So you know eigenvector and the eigenvalue must satisfy ax equal to lambda x, and then you move it around. So ax minus lambda x needs to be 0, and lambda x is lambda times identity times x, and then by linearity, this is a minus lambda I x equal to 0. Okay, and so eigenvector is a non-zero vector. I guess yeah, it's non-zero here. We didn't stress, but eigenvector need to be non-zero so that you can span actual non-trivial subspace. And yeah, so eigenvector is non-zero. That means non-zero. That means it's A. So we can look at this A minus lambda I together as a matrix, and so this matrix has some non-zero solution to this A prime x equal to 0, and this is something we studied since chapter 1. So okay, yeah, and so lambda is an eigenvalue if only if this has a non-trivial solution, and this means that the null space of this A minus lambda I is non-zero, and also a whole bunch of properties we have. For example, this must be a singular matrix. Okay, and yeah, but anyway, then we know what are the eigenvectors related to lambda. So if x is eigenvector related to lambda, then this equation must be satisfied. That means that x is inside the null space of A minus lambda I. Okay, and yeah, yeah. So just what we said. So if lambda is the eigenvalue of A, then this A minus lambda I must have non-trivial equal A minus lambda I times x equals 0 has a non-trivial solution, and it means the null space has a non-trivial vector. And so the non-trivial vectors are all eigenvectors associated with lambda, and anything inside an eigenvector. And so from this equation, we see that the eigenvectors are forms a subspace, and they are called eigenspace. Okay, so I guess if you want to be very picky, then there is a little different. So eigenspace are actually not the eigenspace are all the eigenvectors associated with lambda, but the eigenvector also need to be non-zero. So eigenspace is just a little more than all the eigenvectors. All the eigenvector plus the zero vector. just a little technical thing. And okay. And okay, so back to the thing that we already spilled. And so that's about eigenvector, and what about the eigenvalue? So you want the eigenvalue. You want lambda to be eigenvalue means that A minus lambda I is singular, and from what we already know, this means that the determinant equal to 0. Okay, and so now this is the equation you can calculate. So if you know A, and so you think lambda as a variable, then you can calculate this determinant. You can write an algebraic expression for this thing, and this equation we'll call the characteristic equation for your matrix A. And actually, so they say we treat lambda as a variable because lambda is something we want to find. We want to find lambda such that this thing is actually 0. And so if you treat lambda as a variable and you expand out this equation, then it's actually a polynomial in lambda. Okay. We'll see an example soon. What is a polynomial? Okay. So this is a polynomial in lambda, and so instead of characteristic equation, usually we call it a characteristic polynomial. Okay. Yeah. And yeah, so the characteristic polynomial is the thing you want to solve. So you want to solve this, I guess it's different. So this is a polynomial in this equation. Okay. And the characteristic equation, so the polynomial is just the left-hand side of this determinant. Okay. So the characteristic equation is basically saying P of lambda equal to 0. So this is characteristic polynomial equal to 0. And then we have a polynomial equal to 0. Then hopefully from high school algebra, you remember that. Then that means you want to solve the roots of the polynomial. Okay. Okay. And yeah, so solving the characteristic equation is solving for P of lambda equal to 0. P of lambda equal to 0. And so those solutions will be the roots of the polynomial. And so now we know the roots of this characteristic polynomial is the other eigenvalues. And so how many eigenvalues are there? Those things are a bit tricky because eigenvalues and eigenvectors can actually have a complex complex coefficient. So if you allow complex number, and that makes more sense in terms of eigenvalue. Okay. So if you have if you allow complex eigenvalues, then this polynomial will have n roots. Where remember A is n by a matrix. Okay, and also something we didn't say is the polynomial you can easily verify that is nth degree. Okay, so this is a degree n polynomial, and by I think the fundamental theorem of algebra, you can always show that the polynomial will have n roots. Okay, and yeah, so there will be n complex eigenvalues. Okay. Okay. Although as we will see, maybe not today, but in 6.3, which is the next subsection, we'll see that so polynomial have n roots, but some of the roots will be the same, and then we'll have more complicated yeah, we'll have a more complicated situation there, and we'll explain. Okay. But for now, we know we have n complex root, and but being complex here is also weird because we've been spending the whole semester talking about real coefficients and everything being real, but this is where we need to deal with some complex value, okay? Because this is much more nature. Okay. Any questions so far? Let's go to the summary page. Okay. And so summary page. So we start with for every A being n by a matrix, and And the lambda we think it might be eigenvector, eigenvalue, and so the scalar eigenvalue, then we have the following equivalence. Okay, so if lambda is the eigenvalue of A, then we see that from the eigenvalue equation we have Ax equal to lambda x for some x. That means that A minus lambda Ix equal to 0 with some non-trivial x. And then this means that the null space of A minus lambda I is this non-trivial x, so it's not all 0. And the null space is, and this also means A minus lambda I is singular. So, yeah, and that means the determinant of A minus lambda I is 0. Okay. And so from here, then we can solve. And this is called a characteristic equation, and we can solve a characteristic equation to get eigenvalue. Okay, so that's the example. Probably was also seen in high school. So we have this matrix A equal to 3, 2, 3 minus 2, and we solve for the characteristic equation A minus lambda I equal to 0. And then we first say determinant of A minus lambda I equals 0. And then we have A minus lambda I, A is this, and lambda I is this. So basically get a minus lambda on the diagonal term. So we have 3 minus lambda, and 2 is 2, and 3 is 3, and minus 2 minus lambda. Okay, and we want to calculate the determinant of this thing. And 2 by 2 matrix determinant is 2 by 2 matrix determinant is easy, so it's these two terms minus these two terms. This two term tensor product minus these two term product. Okay. And so that's 3 minus lambda times minus 2 minus lambda, and minus of diagonal product, so minus 6 is equal to 0. And here we set up the number nicely, and so you see that you will expand it out, then we have lambda square, and here we have plus 5 minus 6, so minus 1, and minus 12 equal to 0. And so we actually can factor this into two nice integers. So this is lambda minus 4 times lambda plus 3 equals 0. And so first lambda is this 4, and second lambda is this 3. Okay. So this is lambda square, so about soundness, this is lambda square minus lambda minus 12, or lambda minus 4 times lambda plus 3. Those are characteristic polynomial, and those polynomial equals 0 is a characteristic equation. Okay. And as we see, we solve this polynomial, solve this equation, and get the two roots of this polynomial, and the roots are 4 and minus 3. So those are our eigenvalues. Okay. And yeah, let's continue with the calculation. So we have the eigenvalue, then we want to find the corresponding eigenvector. So A minus A. So we want to find the null space of A minus lambda I. And so first lambda I is 4, and A minus 4i. So let's calculate the A minus 4i first. And is 3 minus 4, 2, 3, and minus 2 minus 4. And then finding null space, we have been doing this a lot this semester. So you just say this equation times x1, x2 equals 0, and you do Gaussian elimination, etc. Okay, and but I guess here we are being lazy about. Okay. Yeah. So our A minus 4i is minus 1, 2, 3, and minus 6. And so we skip a little bit, so you can do Gaussian elimination, and you see 0, 0 here. And so you get minus 1x times 2x2 minus 1x1 plus 2x2 equals 0. So we just have x1 equal to twice of x2. So x2 is some alpha, then x1 is 2 alpha, and is alpha times 2, 1 is eigenvector. Okay, and so you know this eigenvector belonging to or associated with lambda 1, eigenvalue lambda 1 equal to 4. Okay. And then the next eigenvector is similar, so lambda 2 equal to -3, and then your a minus lambda I is a plus 3i, so diagonal got plus 3 plus 3, and there you got 6 2 and 3 1, okay. And yeah, so this thing once again, then you see 3x1 plus 1x2 need to be 0. Okay. And that means -1. Here we are being a little different, but okay. But anyway, you see this minus alpha and 3 alpha will be eigenvector because 3 times minus alpha is minus 3 alpha, and 1 times 3 alpha is 3 alpha, so it cancels out. And so it's alpha times minus 1, 3. It's an eigenvector. It's an eigenvector belonging to minus lambda 2 equal to -3. Okay. Any question about this example? If not, okay. So this is a very straightforward calculation, but we are running through this slowly to get you more familiar with it. And yeah, those kind of calculation we'll do a lot in this chapter. But anyway, if there is no question, then let's go to even more calculation. More calculation with a bigger matrix. Now it's harder to calculate. Yeah. So A is 2 minus 3 1, and 1 minus 2 1, and 1 minus 3 2. And once again, we solve our characteristic equation. So we solve this delta determinant of a minus lambda I equals 0. And so it's a determinant of a and minus lambda I just means the diagonal term get minus lambda all of them. Okay. And so you need to calculate the determinant of this thing. And okay, and we skip the intermediate here. But I guess we can do slow calculation because why not? I think we have a bit of time. So the calculation will be, let's see if I can do this here correctly. So it will be 2 minus lambda minus 2 minus lambda and 2 minus lambda. So this term plus minus 3 and plus minus 3. And then we need to minus the other diagonal. Okay. And minus 2 minus lambda times minus 3, and minus those three things, minus 3, 2 minus lambda, and then minus 2 minus lambda, and this whole thing is please be quiet. Okay, so this whole thing is so those two, so it's lambda squared minus 4, 2 minus lambda, and minus 6, and those two terms plus 6 times 2 minus lambda, and plus lambda plus lambda plus 2. This is very complicated, and this is okay, let's try this slowly. Minus lambda cube, and plus 2 lambda squared, then plus 4 lambda, and minus 8, then we minus 6, and then this thing is minus 6 lambda plus 12, and finally we got plus lambda plus 2. Okay, are we careful enough? So we have minus 14 here and plus 14 here. Okay, so we paste the first thing, we get rid of the constant term. And the other thing is lambda. So lambda times minus lambda square, and this term plus 2 lambda, and finally first order term. This is 4 minus 6 plus 1, so it's minus 1. Minus 1. Okay, yeah. And so we are correct. So it's lambda, and you take out minus sign, this thing is lambda minus 1 squared. Okay, so you see the calculation can be very complicated, but I guess, yeah, so it will be painful in homework and test, but if you think about your computer science department, then when you actually do work, you can use the program to do the calculation. And anyway, now back to only being in math class. This is a painful calculation, but yeah, you can do it. Okay, and so back to the mathematics. So you do the calculation, and you see the characteristic polynomial can factor into this lambda and lambda minus 1, lambda minus 1. So you see that now we have 3 roots. Okay. And the first root is lambda at 1 equals 0. And now we have this degeneracy in roots. So we have 2 roots the same. Okay. Lambda 2 and lambda 3 equal to 1. Okay. And the first thing, lambda 1 equal to 0. Okay. Lambda 1 equals 0, and so a minus lambda 1 I is just your a. And so you just want to solve a equals 0. Okay. And ax equals to 0. Now we write in these arithmetic equations, so there's this thing to write. And x equals 0, and well, excuse me. Ax equals 0, and so you write this. How do I say? Excuse me. So you do this Gaussian elimination. And Gaussian elimination, and you are left with this thing. Okay. Yeah. And yeah, so we also skip the middle step of Gaussian elimination. And so anyway, we got this matrix equal to this arithmetic equation. So 1, 0, minus 1, and 0, 1, minus 1, 0, 0 times your x vector equals 0. And so here now you see this x3 is free variable, so you say x3 equal to alpha, and then you see x1 and x2 must also equal to alpha. And so your null space solution is alpha times 1, 1, 1. So your eigenvector, so the eigenspace is everything in terms of alpha 1, 1, 1, and the eigenvector is something proportional to this 1, 1, 1. Okay, and so how about lambda 2? So lambda 2 is 1, and there is twice root in it. Okay, and anyway, so a minus lambda 2i. Okay, a minus lambda 2i is a minus I. So your diagonal, you get a minus 1. Yeah. And yeah, so your diagonal get a minus 1, and so you get this very symmetric equation, very symmetric matrix. So minus 1, so 1 minus 3, 1 minus 3, 1, 1 minus 3, 1, 1 minus 3, 1, all 3 rows. Okay, and so once again you solve this a prime x equal to 0, and so Gaussian elimination, because the 3 rows are the same, and these 2 rows just get eliminated, and so you see both your alpha 2 and so both your x2 and x3 are free variable here. Okay, so we pivot is x1. Okay, and so now you have two eigenvectors. The first one is pivot from taking x2 free as alpha, and then you get alpha times 3 1, and the second one is taking x3 as free, and so you see x1 need to be negative x3, so you get minus 1 0 1 times 0 beta. Okay. So the eigenspace is spanned by those two vectors, and the things inside eigenspace can be written as alpha times 3 1 0 and beta times minus 1 0 1. Okay. Any question about this more complicated example? Not? Then let's go to next example. Okay, now this is more complicated because it has a complex value. Okay. So we have a very simple A, and A is 1, 2, minus 2, 1. So once again, we solve our characteristic equation, determine of 1 minus lambda, and 2 and minus 2, 1 minus lambda, and is diagonal square, 1 minus lambda square, and minus 4, so it's plus 4, and yeah, and so if we expand all this, then it's lambda square minus 2 lambda and plus 5. Okay, and yeah, and let's try to solve this a little slower. So lambda plus minus is 2a, 2, so 2a is 2, and minus b is 2 plus minus b squared minus 4ac, so 4 minus 20. Okay, so everything can be divided by 2, so it's plus minus square root minus 16, and so it's 1 plus minus 2i. Okay, and yeah, so now we know we have complex value here. So our two eigenvalues are 1 plus 2i and 1 minus 2i. Okay, and well, then now we just pretend that we know how to do complex Gaussian elimination. So, well, so anyway, I guess not only pretend. So now we need to do complex Gaussian elimination because a minus lambda 1i is this well, it is a complex matrix. Is minus 2i, 2, and minus 2, minus 2i. And so we need to do complex Gaussian elimination, but it's basically just so here I will just state these are true. So you can do Gaussian elimination on complex value, just that all the multiplications can have complex coefficient, and you can still do Gaussian elimination. Okay. So yeah, so you can do like so you can just also subtract the first line to. You can also multiply some vector of first row to the second row to eliminate, and it should be. So if you add this thing with, I think if you multiply by I over first line, then this thing become plus 2, and so that will cancel with this minus 2, and this become 2i, and so 2i minus 2i become 0. Okay, so you just do Gaussian elimination with complex numbers, and you can still get a complex value reduced row echelon form. Although here we don't do a normalize because it's not quite necessary. Yeah. So, but anyway, you can still eliminate this row, and then you got this minus 2i and 2. And then you solve this, and then you can just say the x1 equal to alpha. Then you get minus 2i alpha plus. Okay, so if you just say the x1 equal to alpha, then you get minus 2i times alpha plus 2x2 equal to 0, and you get, so you can cancel those two, and then you just get x2 equal to alpha I. Okay, and yeah. So you just do everything with complex value, and this is why do we get so many? And yeah, so this is alpha and alpha I. And so you take a lot of alpha as before, then you see your eigenvector is 1i. Okay. So yeah, it's more knowing this even if you start with a real matrix, your eigenvalue and eigenvector can be complex value and complex vector, but that's what it is. Okay. And yeah, so this 1i is the eigenvector corresponding to eigenvalue 1 plus 2i, or if you want to talk about eigenspace is alpha times 1i. And okay. But now things are more tricky because although we will not push you too much into this detail, but now we talk about eigenvector is in a complex vector space. Then it's not really weird to talking about alpha only real number. Okay. So now we are in complex vector space, then this alpha this every scalar should be complex value. So now alpha is also a complex number. Okay. But yeah, there's some detail that we will not push into. But I guess it shows that sometimes you need to deal with complex number. Okay. And yeah. And so in this, so alpha is a complex number, but this is still a one-dimensional space spanned by this 1i. Okay. Okay. And then the second eigenvector, lambda 2 is 1 minus 2i. And now things are similar. A minus lambda 2i is now, so the is the plus 2i, 2 and minus 2i. And then you can multiply the first line by minus I and add to the second line. And then you can do Gaussian elimination. So times minus I and I times minus I is plus 1. So then 2 minus 2 becomes 0, and this is minus 2i and plus 2i integrate to 0. And yeah, so you do Gaussian elimination, and you're left with 2y and 2. Okay. And then you similarly try to solve this times x equals 0, and you find out that so you say the x1 to some alpha, then your x2 need to be minus alpha times I. And so your eigenspace is this complex alpha times 1 and minus I. And so this 1 minus I is the basis for your eigenspace associated with lambda 2 equal to 1 minus 2i. Okay? Any question about this complex number example? No? No, okay. So now we semi-know this complex vector space. Yeah, it's a bit annoying because we have been talking about everything in basically real scalars, but now we are in even we have a real matrix, we will have complex eigenvalue and a complex eigenvector we see here. So we kind of need to know how to deal with complex vector space. But as you see here, hopefully you can feel that doing Gaussian elimination in complex with complex coefficients is basically same as doing Gaussian elimination for real coefficient. So you just do the same thing, but you can now multiply by a complex number, etc. Okay, and then complex vector space is a bit more weird as we see the inner product is different, but this I guess the linear combination part is still same as with real scalar, so you just multiply by some complex number, and you can multiply by a complex number, and you can add the two complex vector, etc. Okay. Okay, then if so, then let's go out of the detail about how to do complex vector space and talk a little other thing. Okay, so so if our matrix is a real matrix, as we see, we can have complex roots, but there is still something you can know from having every entry is real. That is, the complex root must come in conjugate pairs. Okay? And that is, if you have a plus bi as an eigenvalue, then a minus bi must also be an eigenvalue. This is something from analyzing polynomial. So you have a real coefficient polynomial, then you have a real coefficient polynomial, then the complex roots must come in conjugate pair. And this is what we see in this example. So if lambda 2 is 1 minus 2i, and lambda 1 will be 1 plus 2i. So we are in this conjugate pair. Okay, and then here we just have some notation. So if you have a complex matrix or complex vector, then we write a complex conjugate by writing this bar over it. Okay, so A is a matrix with constants number, then A bar is the same matrix, but every entry is complex conjugate. And so maybe let's write an example. Have A equal to 1i 0 1 minus i, and then a bar will be, so you get a minus sign before every I, so 1 minus I 0 1 plus I, etc. Okay, and then it's easy to see that if A, B are complex matrices, and then you can have A times B, then A times B complex conjugate will be A complex conjugate times B complex conjugate. This basically comes from complex conjugation, goes through addition and multiplication. Okay. It's pretty easy to check if you just think about the entries of AB. Okay. And so we have this notation, then we can say a little more thing. Okay. So we just say that the eigenvalue comes in conjugate pairs, and actually the eigenvectors then will also come in conjugated pairs. Okay. So here the important thing is the eigenvector. Okay. So we say if lambda is a complex eigenvalue, and for a real matrix A, and z is the eigenvector of lambda, then we know lambda bar will be an eigenvalue, and actually the associated eigenvector will be z bar, as we see here. And so az bar will equal to a bar z bar, because a is real, so a bar equal to a. Okay, and as we say, a bar z bar equal to a z bar, because this thing we say. Okay, a bar z bar equal to a z bar, and but az is from the eigenvector equation, so az should be lambda z. And so this is lambda z bar, and then this is lambda bar z bar. Okay, because you can kind of think lambda as a one-dimensional matrix and use. Okay, really. This. So you see that. So we go from here to here, then you see z bar is the eigenvector with eigenvalue lambda bar. Okay. So complex eigenvalue, they are annoying, but I guess here is something good about it. So you find one of them, you also find the other, another one. Okay, you can find the complex eigenvalue and complex eigenvector, then you immediately know another complex eigenvalue and another complex vector. Okay. yeah, and let's check again the example. That's correct. So is 1I is eigenvector, and its complex conjugation is 1 minus I, and yeah, so we see this works out. So any question? Yeah. So once again, your matrix is real, and that doesn't mean your eigenvalue and eigenvectors are real. But when they are complex, then because A is real, then you have this HR structure such that your complex eigenvalue and the complex eigenvector complex eigenvalue and the complex eigenvectors come in pair. So if some complex eigenvalue and a complex eigenvector, then their conjugation, complex conjugation also complex is also a pair of eigenvalue and eigenvector. Okay, and okay, and then now let's talk about a little more identity we can know about the eigenvalues. Okay. Okay. Yeah. And so I guess it's easier to wait. Okay. Yeah. So yeah. So we know how to find the eigenvalue. Eigenvalue is you solve the characteristic polynomial, but there are also a little more property that's useful to maybe do some quick check on your calculation. Okay. So actually you can know the product and the sum of the eigenvalues from your matrix A by some really quick calculation. Okay. So let's first see the sum. Okay. And okay, actually they are together. But we are in 4 minutes. Well, I guess let's try to go through how much. Well, anyway, so let's go through this what this characteristic polynomial is. Okay, so characteristic polynomial is determinant of this matrix. We'll see. So we are writing all the whole A matrix are those Aij. So A11, A21, da da da. And as we know, this minus lambda is you put the minus lambda on the diagonal. Okay, and then as we see in our calculation example, you see this is going to be a polynomial in lambda because you are basically multiplying those entries, and those entries are all polynomial in lambda. And you have a product, and the sum of polynomial is still a polynomial. Okay, and anyway. Our definition determinant is we have the recursive definition where we can expand every row and column, and now we try to expand on first column, and we see that is this thing is the first element A11 minus lambda, then expand on this minor, okay, and A11 minus lambda and times the determinant of this submatrix, and then you sum over all other things. So those AI1, so this A21, A31 all the way to AN1, and times their corresponding times their corresponding minor, which is this minus 1 to the I plus 1, and the determinant of the corresponding submatrix. Okay. And I think the name minor here is a bit wrong, but anyway, the minor, or I should say probably the minor of, anyway, but what we want to say here is that, so now we want to count the degree of this polynomial, so we say it's a polynomial, okay. So if we so what we want to say is the only thing that has a very high order term of lambda. Okay, so we think that this will be this whole polynomial will be, so we're counting degree, right? So the whole polynomial has degree n, right? Because there will be, so you keep expanding the first column, and there will be a term that multiplying all the diagonal term, and you know all the lambdas are on the diagonal term. Okay, so the highest order term is degree lambda, but okay, and sorry, highest order term is degree n. Okay, so then will be degree n minus 1 term and degree n minus 2 term. And what we want to say here is that, so we kind of want to look at the degree n minus 1 term, and we want to say the degree n minus 1 term only come from here. And this thing doesn't, so all those summations, or those expansion from a to 1 and da da da, they don't contain, they are at most degree n minus 2 in terms of lambda. Because, okay. So if we, so if we fix some I here, so what we want to say here, if we expand on some AI1 here, right? So we fix on I here, and because what you get from minor is you will get rid of this row and this column, and this means this term is getting picked out, and this ith diagonal is getting picked out. Okay, so yeah, because the determinant Nij, this matrix just don't contain this two term, and so you are missing this element, this lambda here, and this lambda here. So you are missing out at least 2 lambda, and so what we are saying is all those terms, their degree in lambda is at most n minus 2. Okay, and yeah. And I think it's time for break, so let's have a 10-minute break, and let's continue analyzing this polynomial. Okay. And okay, kill the笨掉。让我想想看，有没有怎么？做这里的话，他们会过来吗？ Okay. So let's go back to this detailed analysis of characteristic polynomial. Okay. So we have our detailed, very careful expansion on our characteristic polynomial. So characteristic polynomial is we will want to we want to calculate the determinant of this matrix, and we are trying to analyze its degree in terms of our variable lambda here. Okay, and so as we see, only terms that contain lambda are those diagonal terms. It's a11 minus lambda, a22 minus lambda, etc. All the way to an minus lambda. And so we want to get more lambda, then we need to take more terms. And as our analysis we see that when you expand first column, then you write your polynomial into those terms. Those different, so you have summation over expansion on different element, right? Then you see that you have the term that expand on this first element, and so you get lambda here and the determinant of this submatrix. And then by our analysis, we see that all other terms will getting rid of two factors of lambda, and so all other terms will have degree at most n minus 2, so they will not be degree n or degree n minus 1. Okay, and then you keep going, and you will see that then on the you try to expand the determinant of m11, which is expanding on this submatrix. So let's maybe try to draw here. Then you try to expand on this n11, then you expand on this submatrix that start from a22 minus lambda. And then you still expand on the first column, you still see that only expansion on this thing will have a degree n minus 1, etc. Okay, and so then in the end, you see the thing that the only term that has the highest degree is the term that multiplying all the off-diagonal terms. That is, you keep expanding on the first element of first column. Okay, so just having the same similar analysis, you see that if you want to have a degree n or n minus 1 at the end, the only term that contributing to it is the product of all the diagonal terms. Okay, and so it's the only term with a product of more than n minus 2 diagonal, and that means the degree in the polynomial. So, and the degree greater or equal to n minus 1. Okay, and okay, so then this is the only term that has a degree more than n minus 1. So now we can have a pretty succinct expression for the degree n term and the degree n minus 1 term. Okay, so the degree n term here is from here, so it's a product of lambda here, so it's just minus 1 to the n. Okay, and the degree n minus 1 term is also from here, but you can miss one of the lambda, and so you pick one of the a and all other lambda. So it's minus lambda. Okay, so we write this in funny form. So we say the coefficient of the minus, so you pick n minus 1 lambda here, so it's a minus lambda to n minus 1, and then you can pick other a, and you need to sum them all together, so it's summation ai. Okay, so those a are, remember, it's the original diagonal element of a. Okay, so you have sum ai. Okay, and okay, and now we think about p of lambda in terms of its roots. Okay, so we know highest order coefficient and the second highest order coefficient, then we can talk something. We're talking about different thing. Okay, so we can know the sum of its roots. Okay, and let's compare this. So we say it's a polynomial, and we say we write out it as its roots. So the highest order coefficient is -1 to n, so let's take it out, and then we have n roots here. Okay, and yeah, and we multiply it in, and it's just first root minus lambda, second root minus lambda, etc. And still fail. And okay. And I guess let's go this one first. Okay. And then we can see the sum of all those roots. Okay. So if you multiply this out, then you see the second order term is actually sorry, not the second order term. The degree n-1 term is also equal to sum of all those roots, right? So if you just multiply this out, then you see, yeah, you multiply this out, then you see the coefficient to this minus lambda to n-1 is the sum of all those lambda I. And from our analysis before, we also see that that's in sum of those diagonal term of A, sum of I. Okay. So yeah, so this is the equation that we can get from all the analysis before. So sum of all eigenvalue will equal to, this is actually very easy to calculate thing. This is the trace of A. It's just sum of the diagonal term. Okay. It's called the trace of A. Just adding all diagonal terms together, it's very easy to calculate. Much easier than calculate determinant. But if you calculate determinant, then you can get something else. So there is something else that we don't need to do all those. Something else we can know about the eigenvalues is that the product of eigenvalues is just okay. So we put lambda equal to 0 here. Okay. So this equation you don't actually need to do all those analyses to get. You just need to write down a characteristic polynomial, or I guess you need to. Sorry, you need a little bit. So this equation, you need to analyze enough to know that the highest order coefficient is -1 to the n. Okay. So if you know this, then you pick, and then you pick that lambda equals 0 here. Okay. And then this side become p of 0, and but you go back to all the beginning. Then you think about if the lambda equals 0, then the determinant is just the determinant of A. Okay. Lambda equals 0, you just calculate the determinant of A. Okay. So when you pick the lambda equals 0, then this polynomial should just calculate to lambda of A, sorry, determinant of A. And the other side is just product of lambda, right? It's just lambda 1, lambda 2 to lambda n. Okay. So you see the product of lambda equal to determinant of A. Okay, so yeah, so here we get two things we know. So the sum of lambda, sum of the eigenvalues equal to the trace of your matrix A, and the product of eigenvalues equal to determinant of your matrix, and they are useful now, and those are very mathematical things, and they are important. Although theoretically you can always like just get some A, and you can just brute forcefully calculate all the lambda if that's you are just solving engineering problem. But this is sometimes useful mathematically, and you want to know some property of your you want to show some property of your matrix related to some property of your lambda, to your eigenvalues, and also it's good for checking your calculation. Say you calculate some eigenvalues, and maybe you want to check your answer, then you can see where they add up to trace. So maybe let's go back, and let's see we have eigenvalue 1 minus 2i, eigenvalue 1 plus 2i, and you sum the integrate become 2, and you see the trace of A is 1 plus 1 equal to 2, etc. So this trace is easy to check. Okay, so you can check, and you can also do some algebraic derivation from this. Anyway, let's see more example and to see this is true. Okay. And so we have another matrix A here, A equal to 5 minus 18, 1 minus 1. Okay. And the determinant of A is minus 5 plus 18 and is 13. And the trace is 4. Okay. And the characteristic polynomial is this thing, so determinant of A and the minus lambda on diagonal. And then it's okay, so it's lambda square and let's see, plus 1 minus 5, so it's minus 4 lambda, and minus 5 plus 18, so it's plus 13. And then the eigenvalues, we skip the calculation, and it's 2 plus 3i and 2 minus 3i. And so you add them together, so 2 plus 2 equal to 4. And you multiply together is 2 squared plus 3 squared equal to 13. It's a determinant. So it's just checking this is true. Okay? And okay. And the question, then we go to even very useful theorem. Okay. So it says that if you have two matrices A and B, and B is similar to A, and remember that means that you have some non-singular A's, such that B equal to S minus 1 AS. Okay. And then A and B will just have same eigenvalue because they will have the same characteristic polynomial. Yeah. And so this is the first theorem we show. And the proof is pretty straightforward. So you think about the characteristic polynomial of B is determinant B minus lambda I. Okay. And then we use a similar equation, B equal to S minus 1A minus S, and minus lambda I. And then I, okay, so we have a lot of S minus 1 here, so we also put S minus 1 here. Try to put S minus 1 and S here. And you can do this because identity is equal to S minus 1 identity times S, because S minus 1 times S equals to identity. Okay. And yeah, so you can just get free S minus 1 S around your identity. And then now you can get linearity because it's S minus 1 times something times S, and S minus 1 times something times S. And then it's just S minus 1, and there's A minus lambda I times S. And then now we use something we say is very important and useful but never used. And that is the determinant of product of matrices equal to the product of determinant. Okay. So it's very important that we check in midterm. Okay. So it's a determinant of those three matrices S, and A minus lambda and S, and it's a determinant of S minus 1, determinant of A minus lambda, and a determinant of S. And okay. And then determine. Then the next step you can do multiple things. But first, basically determinant of S minus 1 will equal to minus 1 will be 1 over determinant of S. So those two things cancel out. Or you can also check this by just thinking. Because now, remember, determinant is a number. So number you can multiply by every order. So this thing is just determinant of S minus 1. Those two terms together, determinant of S minus 1, determinant of S. And this is equal to determinant of S minus 1 S. Oh, actually, wait. Oh, yeah. And this is determinant of identity, and this is equal to 1. Okay? And yeah, so now those anything cancel out. Then this is determinant of A minus lambda I, and it's a characteristic polynomial of A. Okay. And yeah, so those two matrices, they have the same characteristic polynomial, and so they'll have the same eigenvalue, but I guess it's a little important to say they don't necessarily have the same eigenvector. Okay. They can have a different eigenvector, but they have the same eigenvalue. Okay. Yeah, because the characteristic polynomial only told you about the eigenvalues, and yeah. So I guess these two matrices. What I'm saying is those two matrices, they have the same determinant, but they can have different null space. Okay. And anyway, let's see an example. So T and S. Okay. So T is this matrix 2, 1, 0, 3, and S is this matrix 5, 3, 3, 2. And the characteristic polynomial of T determinant T minus lambda I. So 2 minus lambda times 3 minus lambda, and the other thing is 0. So now this is already in factorial form. So you already read lambda 1 equal to 2 and lambda 2 equal to 3 here. Okay. And oh, okay. So we have T here, and we try to see a similar matrix. And so we have another matrix that's similar to T by multiplying S minus 1 and S on the two sides. So S minus 1, so determinant S equal to 1, and so S minus 1 is easy to write. It's a Kramer formula, so 2 here, 5. So you swap those 2, 5, and the off diagonal, I think you get a minus sign. Okay, so S minus 1 is 2 minus 3, 3 minus 3, 5 matrix. And so you multiply by T and then multiply by S, and we skip the calculation, and we get this A equal to minus 1 minus 2, 6, 6. And then once again we calculate the determinant of A minus lambda I equal to 0. And yeah, and that's minus 1 minus lambda times 6 minus lambda, and plus 12 here, and that's this lambda square, and 6 plus 1, and wait, minus 6 plus 1, so minus 5 lambda, and minus 6 plus 12 equal to 6. And yeah, so once again it's the same polynomial, it's lambda minus 2 times lambda minus 3 equal to 0. So eigenvalues are also 2 and 3. And let's see whether the thing I say is true. Okay. So I say that they will have different eigenvectors. So let's try to check. So say with lambda equal to 2 thing, then the eigenvector here want to check T minus 2i. So T minus 2i equal to 0, 1, 0, 1. And so the eigenvector will just be 1, 0. Okay. And let's check again. So 1, 0 times T is 2, 0. Okay. And then is 1, 0 eigenvector of A. It's not. Because 1, 0 times A is minus 1, 6. It's not the eigenvector. And but so what's the eigenvector of A with respect to 2? So A minus 2i is minus 3, minus 2, and 6, and 4, and you do Gaussian elimination, you get minus 3, minus 2, 0, 0. And so the eigenvector is, so basically something orthogonal to this, and the eigenvector will be so alpha times some alpha times 2 minus 3. Okay. And yeah. So eigenvector here is 2 minus 3, and here is 1, 0. They are not the same. Okay. But it is still nice to know they have the same eigenvalues. Okay. And sometimes it's called anyway. Yeah. And so this is 6.1. I guess this is the most important part of this whole chapter. That is knowing what are the eigenvalue and what are the eigenvector. Basically, you go to this definition, and you need to know how to calculate it. We give a lot of very explicit example of how to calculate the eigenvalue and eigenvectors. Okay. And so once again, the eigenvalue and eigenvectors are defined by this equation, and so A is a square matrix, then A is n by n, and then eigenvalue and eigenvector satisfy this equation. Ax equal to lambda x, where x is your eigenvector and lambda is your eigenvalue. Lambda is a scalar and x is a dimensional vector. And from this equation, you can see that A minus lambda x equals 0. And so there are a whole bunch of things this A minus lambda, we can say about this A minus lambda matrix. Okay. So it has a non-trivial solution, and it means that its null space is non-zero, and it means it's a singular matrix, and it means its determinant is 0. And determinant equals 0, then we can think about lambda as so determinant of A minus lambda equals 0, we can think of this as the equation in terms of unknown, not equation, expression. This whole thing as an equation in terms of unknown variable lambda, and the determinant will be a polynomial in lambda with degree n, and and yeah, so the polynomial is a characteristic polynomial, and so for this characteristic equation we can get lambda. Okay. And as you see, because we are still confined to real A, so even though A is real, lambda can be complex, and but A is real gives some restriction on our complex lambda. So if you have a complex eigenvalue, then its complex conjugate is also the eigenvalue, and also if you have eigenvector z here, and z bar will be associated eigenvector. So and so it's kind of a pair lambda z, then also lambda bar z bar is a pair. Okay, and then we have more properties. The property we just derived. So we say that the product of all eigenvalues will equal to determinant of your matrix, and the sum of all your eigenvalue will equal to the trace of your matrix. So basically, the sum of the diagonal element. Okay. And then we derive that if a matrix B is similar to A, then they will have the same set of eigenvalues. Okay. Any question so far? If there is no question, then we'll jump a lot. Wait, but let me say a little bit. So this is the characteristic equation, and you solve this thing for your eigenvalue lambda. Okay, let's box these out. Okay, if okay, then we have about 30 more minutes. So let's try to, let's see. I think the schedule is a bit weird, but I think scheduling is okay. But also, once again, as a reminder, I'm traveling abroad next week. So I think what we'll do is I'm just going to do a video lecture. We'll pre-record video lecture. You can look online, but I will try to limit that. So we'll probably just have about 2 hours, or if we get enough scheduling on this week, then we can cut down what the amount of video you need to read. You need to watch next week. Okay, and yeah. So next week will be a little easier, but this week might be a little tougher. Okay, and so yeah. So let's go to a tougher part. So the next thing about this chapter, diagonalization. And so what do we mean by diagonalization? So it follows from this form. Okay. So we say B is similar to A, then they have the same eigenvalue. And also we say B have the eigenvectors are different. So how about we find B such that it's similar to A, and its eigenvectors are the easiest possible. The eigenvectors are the standard basis. So your D is a diagonal matrix. Okay. And yeah, we find out that we can do this diagonalization a lot of time. Sometimes you cannot. But if matrix A is good enough, then you can get this diagonalization. And this tells you quite a bit about the eigenvalue and the eigenvectors of A. Okay. So anyway, the diagonalization, the idea is you want to find the matrix X such that A equal to XD X minus 1. Okay, so I guess I should write down here. So A equal to XD X minus 1, and D will be, and as we say, A and D will have the same eigenvalues because they are similar, and D is diagonal. So if you are diagonal, then all your, I guess we didn't say, but it's pretty obvious that if you are a diagonal matrix, all the diagonal elements are eigenvalues because the standard basis will be your eigenvector. Okay, so D will be the diagonal matrix with all its eigenvectors on diagonal. And then, as we said, then those eigenvalues will also be the eigenvalue of A. Okay. So yeah, that's a very cool thing to have. And then before we go down, let's go to this theorem 6.3.1. Oh, I guess I should say something before. So we jump from 6.1 to 6.3. Because 6.2 is more like an application. 6.2 is about differential equation, and I think it's more about calculus than it's more about application in calculus. So we skip 6.2. Okay. Okay. And yeah, so let's go to this theorem 6.3.1, and it's a theorem that help us do diagonalization. Okay, so it says that we have undistinct diagonal. If our eigenvalues are all different, then then the corresponding eigenvectors will be linearly independent. Okay, so this is some structure on eigenvectors we can say. Okay, and here we have a schedule of proof. So it's a proof by construction. So suppose you have distinct eigenvalues, and the eigenvectors are not all linearly independent. And so what we do is we prove by contradiction, so we assume these things are linearly dependent. So some are linearly dependent. But to make it easier, so we want to find which one make it linearly dependent. So we kind of go from left and right, and we pick in the vectors one by one, and look at the set, and try to start from which vector we are being linearly dependent. Okay, so then we say that if the first R, if the R minus 1, the R plus 1 vector is the one that make everything linear dependent, that means that so you have this the first R things, they are still linearly independent, and so we find the boundary of making things linearly dependent, right? Linearly dependent. So it's like x1, xr, then xr minus xr plus 1, and So we don't care other thing. So we are trying to expand our set from here to here, and then we say up to here, all the things are linear independent, and then we include r plus 1, then things become linear dependent. That means that r plus 1 doesn't span anything any bigger space, and that means r plus 1 is inside the span of this x1 to xr. Okay, and so we can write this thing. So xr plus 1 is in the span of x1 plus xr, and it has this linear combination in terms of x1 plus xr, x1 to xr, and but also x1 to xr is linearly independent. Okay. And so this expansion should be this expression should be unique because x1 to xr they are Li, so they are basis for whatever space they span. Okay, and then now you just apply your A on both sides of this equation. So you say, what happens if you apply your matrix A to those the two sides of this equation? Okay, and okay, so A on xr plus 1, then you will get well, it's an eigenvector, so you will get lambda I plus 1 here. And so you can also multiply A inside, and then you get lambda 1 on 2 to lambda R here. Okay, and so you can move things around. Oh, I guess. Okay, so here there are only actually two things, and so it's only a sketch here. Okay, but so here there are two possibilities. So if but I guess that is still right here. So there is another case of lambda r plus 1 equal to 0. Okay. Okay, so if lambda r plus 1 equals 0, then that means it's monoid. That means this side is 0. But this side will not be 0 because we say all the lambda are distinct. So all the lambda 1 plus 2 lambda are not 0. And so you get non-zero coefficients of those things adding up to 0, and that's a contradiction because they are linear independent. You cannot have a non-zero coefficient adding up to 0. Okay, and then the more general case, if lambda r plus 1, I should not say I plus 1. Sorry, so here is wrong. So lambda r plus 1, lambda r plus 1. Okay, so it's not 0, then you can divide it to the other side. And then you can write a whole bunch of C1 prime, C2 prime to CR prime, where the C prime is Ci lambda I divided by lambda r plus 1. But you know lambda r plus 1 are not equal to those lambda I for AVI. And so all those coefficients are different. And then you get a different coordinate in terms of this basis for your xr plus 1. And that contradicts the uniqueness in this coordinate, and yeah, so you see this is impossible. Okay, hopefully this is not too confusing. And yeah, but anyway, so we see that if your eigenvalues are different, then your eigenvectors are kind of separate out, and then the more technical term to say is they are linearly independent. Okay. And so why we want to do this, because if you have a linear independent eigenvectors, then you can do the diagonalization. What I want to say here so here is the remainder of the definition of the diagonalization. Okay, so we are kind of keeping back and forth. So diagonalization is you want to find some matrix X such that x minus ax equal to d, or a equal to xt x minus 1. Okay, and so here is just a reminder of the definition of diagonalization, or it's more like saying diagonalizable. Okay. Diagonalization means you want to do this, and diagonalizable means you can do this. So A is diagonalizable, you can find X such that A equal to X dx, and D is X dx minus 1, and D is a diagonal matrix. And so we want to say A is diagonalizable if only if its eigenvectors are linearly independent. Okay. And here is a bit tricky. So this will be so we say if the lambdas are all different, then the vectors are linearly independent. So this is a sufficient condition for A is diagonalizable by this theorem. So the two theorems together says that if the lambdas are all distinct, then A is diagonalizable. So before we go to proof, let's talk about implication. But this is sufficient but necessary. So even if lambda are not all distinct, A might still be diagonalizable. So you can still have linearly independent eigenvectors. Okay, but yeah. So that's something I want to say about 6.3.1. So here is an easy case to analyze. But if you have some eigenvalues are the same, then things get very tricky, as we will see in the later part of this section. Okay, but let's first prove this theorem. So the theorem is an if-only-if equation, right? So here we say that see that the eigenvectors being linear independent is the thing we want. So eigenvectors are linear independent, then if only if, then that means it's diagonalizable. It's if only if. Okay, so if only if, then we need to prove two direction. So first we need to say linear independent and go to diagonalizable. Okay, and the proof is very constructive. We'll give you an x. Okay. So you have all those eigenvector x1 to xn, and so notation already set up nicely. So we have all those eigenvectors, and remember the vectors are column vectors. And so what is X matrix that to let us do diagonalization is you just list all those eigenvectors together. Okay, so you just have x1 as the first column, x2 as the second column, to xn as the second column, and we say this matrix will be the matrix X that do diagonalization for you. Okay, and so how the okay. So this is our claim, but we need to check that this is actually true. Okay. And yeah, so we need to say x minus 1ax is actually some diagonal matrix. And then we try to show this from the eigenvector equation. So remember, all those x are eigenvectors. So axj equal to lambda xj. Okay. So what we want to find right is this funny equation ax equal to xd. So remember the equation we want to show was that ax minus 1 ax equal to d. And we kind of do this in a middle point. So we kind of move x to the other side and we want to show ax equal to xd instead. Okay, so ax equal to xd. And what is ax equal to xd? Then we write out ax. Okay. And now it's one of the interpretation of different interpretation of matrix multiplication. So you have this. So let's draw a picture. So you have this A matrix here, and then you have this X matrix that's many different columns. x1, x2 to xn. And you can think about the multiplication result is you multiply each column separately. And yeah, so you multiply the first column, then you get the first column, you multiply the second column, you get the second column, etc. So you're just listing all the columns multiplication results separately. This is something that we know from just how matrix multiplication rule will work out geometrically. Okay, and yeah, so the resulting column will be first column will be ax1, and the second column will be ax2, etc. And then by those columns, from the eigenvalue equation, we know this is lambda times x1, lambda times x2 to the way to lambda times xn. Okay, and but this can be written in other form. This is so you are just basically multiplying each column by the eigenvalue lambda 1, lambda 2 to lambda n. And you can do this column multiplication by multiplying the diagonal matrix on the right hand side of your matrix A. Okay? So if you want to multiply each column by some coefficient, you can just multiply by this diagonal matrix over the coefficient lambda 1, lambda 2 to lambda n. And check matrix multiplication rule, and that will be correct. So yeah, you have x, and then you have lambda 1, lambda 2, lambda n diagonal. Then you see that then the first column will get multiplied by this, etc. I guess yeah, it doesn't say much, but you can check the rule yourself and see this is true. Yeah, and then but now what's this matrix? So this matrix is X, and this matrix is a D matrix that we said. So we'll be talking about the diagonal matrix will be this all the lambda matrix. Okay. So yeah, so now you have this AX equal to XD. Okay, very nice. So we know that if your X matrix is a matrix that's just listing all the columns of eigenvector together, then X equal to XD. But we are missing something. Yeah. So we are still missing our. So where do we use the linearly independent? We haven't used that X are linear independent. So this is actually true for every set of eigenvectors. Okay. And what we are using linear independent next step is that we need a linear independent to actually write those two equations are equal. Okay? So this is always true, but only have linear independent we can imply this, because without linear independent, x don't even have a -1. And yeah, so the only place we need to use linear independent is that our x is n vector of n dimension is a square matrix, and so this matrix is non-singular if only if x is all the columns are linearly independent. And so if we are linearly independent, then x will be non-singular, and we can write x minus 1, and so we multiply x minus 1 on both sides of this equation, and then we get x minus 1 ax equal to d, and then we see a is diagonalizable. And yeah, so any questions so far? And okay. And if there are no question, then we do the other part of the calculation. And we want to say this is if only if. And but you kind of already see what is going on. And so basically A is equal to XD always, but if only you get x minus 1, if only if x is not singular. Okay. But anyway, so let's do actual rigorous proof. So the other way we want to say is A is diagonalizable, then you have n linear independent eigenvector. Okay? And so we kind of go through everything backward. So we start with the A is diagonalizable, then we have some x minus 1 x equal to d. So this x matrix now is, so we kind of overload our notation. But this x matrix for now we think is different. Then we will prove it's the same as the x matrix before. Okay. So x matrix now is just whatever thing that satisfy diagonalizing A. Okay. And once again, is x is non-singular and square matrix, and it has columns. Okay. And so we are just going to show those columns will be linearly independent eigenvectors. And this is just from we have this equation, then we have ax equal to xd, and ax equal to xd, as we know, it looks like an eigenvector equation. Okay, so we're basically just running everything in backward. Okay, so ax equal to xd, and that means that ax1 will equal to d11 x1, and ax2 will equal to d22 x2, etc. Okay. And yeah, so we see that actually just from this equation here, we see that every column of this X matrix will be eigenvector of A, because AXI will equal to D IIXI, and yeah, and okay, and now okay, so we find n eigenvectors, and now we need to say they are linearly independent. Then you go back to the similar thing. So because A is non-singular, that means all the columns are linearly independent. Okay, and so we have found the n linearly independent eigenvectors. Okay. Any question? Okay. If not, then let's go to this remark. Yeah, as we said, so if A is diagonalizable, then this diagonalizing matrix is X. They are actually formed by eigenvectors of A, as we have seen in the proof. Okay. So if you just list the eigenvectors into a matrix, then it will be a diagonalizing matrix. Okay. And yeah, you need to have all the eigenvectors that are corresponding to all the eigenvalues of A. Okay. And the diagonal matrix, as we say, the first dot will corresponding to the eigenvalues. Okay. So you will always have n different eigenvalues, but you need to have n different eigenvectors for you to be diagonalizable. And then one important remark is that the diagonalizing matrix, as we define here, is not unique. So here are just two very easy. Here we have two things that you can do on X. Excuse me. Two different things you can do on X to get a different X but still diagonalizing. So first thing is there is no particular ordering on the eigenvalues here, right? So these X only need to be eigenvectors that are corresponding to those eigenvalues. But you can reorder those eigenvalues. Maybe you swap D11 and D21, D22. Then, or more like you swap lambda 1 and lambda 2. Then you will also need to swap x1 and x2 to make X the diagonalizing matrix. And that will also be a diagonalizing matrix, and but that's a different X. Okay. And another thing is we didn't specify the norm of our vectors X. Okay. So all those xi, yeah. So these things will be weird, but it's actually okay. So you can, instead of x1 here, you can have x1 here, then you can have like twice x1 here, and that will still diagonalize in your matrix. And that's okay because basically, or even say you can have x. So maybe you think about all your x multiplied by 2, right? So instead of x, you have 2x, but that's okay because you will still get a sandy back because you have x minus 1 here. So if you have twice x, then your x minus 1 will get 1/2. Okay. So yeah. So you can have a different x and still diagonalizing your A to similar D. Okay. Okay. Yeah, if you reorder x, then you will have a reorder D, and you multiply x, and you will get kind of the same D. Okay, but they are all diagonalizing your A. And we have 3 more things. But I think we are almost out of time. I guess the third thing is the thing we already said. Is from the other theorem we said. So we say that if you have n distinct eigenvalue, then it is sufficient to say A is diagonalizable. N distinct eigenvalue, then every eigenvector is linearly independent, then it's diagonalizable. Okay. And as we said, then if your eigenvalues are not distinct, then you may or may not be diagonalizable. It's not if only if. Okay. And yeah. And I guess this remark is just saying once again is the definition of diagonalizable is that you can write a equal to xt x minus 1. Okay, just in time. So we'll continue on Wednesday and see how much we can teach in this chapter 6. Okay, see you on Wednesday.